Symmetry elements. It's lit.
Hi there, and today we will be talking about symmetry elements and operations. First will be the identity with symbol E. Second, the n-fold proper access with symbol Cn. Next, the plane with sigma as the symbol, inversion center with I, and finally n-fold improper axis with Sn. We hope you enjoy. For the first identity, we have the symbol E, which the operation is it leaves in the original position, so there's no other way that you can rotate it or flip it so that it stays the same. So here is the fire extinguisher that we're using. You can tell that with the nozzle here, along here, that the only way you can get it to look this way is if you do a full 360 degree rotation. It can't flip like that. You can't turn it around an axis or invert it in any way so that it shows up the same due to the rounded top and the flat bottom, the nozzle here. And that's the first example for the identity E.
So secondly, we'll be talking about the n-fold proper rotation, and the object we're going to be using to demonstrate this this element is actually this roll of toilet paper right here. So say, for example, there is the proper rotation axis going straight through the center of this, meaning that you're going to be rotating the object around this axis, some degrees. Now that axis in particular is called a C2, so a two-fold rotation axis. That's what the n value is. And what you're going to do with that value is you're going to do 360 degrees divided by 2, and that'll be 180 degrees. And then, as you'll see here, if I rotate this 180 degrees around that axis, you're going to notice that it appears completely unchanged in space. And that's the whole point of this proper rotation axis. However, it is possible for a molecule or object to have more than one proper rotation axis. For example, this toilet paper again. If you can imagine just putting a proper rotation axis straight down the center here, it's a circle, and so you can turn it an infinitely small amount of times, and it would still appear unchanged, correct? So that's why that rotation axis would be called a C with the subscript infinity, because it can be infinitely small. 360 degrees divided by infinity is an infinitely small number, which is how small we're rotating this the roll of toilet paper here. So that's really all there is to the proper rotations. Next up, we'll be talking about the mirror planes and how you can reflect objects and make them appear and make it look like there's an exact mirror image of itself. So next up, we're going to be talking about mirror planes, and more specifically the three different kinds there are. There's the vertical, horizontal, and the dihedral mirror plane. All three of these differentiate slightly. We'll get into that later, but first I just want to bring in the household item, the calculator that we'll be showing you just to demonstrate the mirror planes. Unfortunately, we actually don't need this calculator part at all. We just need the case, so we can just get rid of that. So yeah, we're just looking at the case here, and if you take a close look, just right down the center there, you can see that, just imagine a mirror just going straight down the center where my hand was there, and you can see that it'll be an exact reflection of itself. That is the definition of what a mirror plane is. However, what kind of mirror plane would this be? Because there's the three different types that I mentioned. There's the vertical, horizontal, and the dihedral. The dihedral and vertical are very similar. They are both collinear with the principal axis. However, there are a few differences. For example, if there is more than one principal axis, so there are multiple axes, then there can't be any dihedral mirror planes. However, there can still be vertical ones, obviously. Also, there are some molecules where you can find both vertical and dihedral mirror planes. But the way to tell those apart is that the dihedral mirror plane tends to cut between the bonds more than the atoms, whereas the vertical mirror plane goes straight through the atoms rather than the molecules, or the atoms rather than the bonds. My apologies. And like I said, both of them are collinear with the principal axis. However, there's the horizontal mirror plane as well. That one is not collinear. It is perpendicular to the principal axis, so that's how you tell all three of those apart. But the question still remains, what kind of mirror plane does this have? And after looking at this for a while, you can actually start to notice that there really isn't a principal rotation axis. Anytime you rotate it around any sort of axis, you would have to do a full 360-degree turn, which is just the identity. It's E. Which is why I would deem this without a subscript even. I would just give it just a mirror plane just straight down the center. It can't be labeled as vertical or horizontal or dihedral if there's no principal axis. And that is all for the mirror planes. I'll pass it on to Brendan now, where he will go on to talk about the last two remaining elements.
The second to last symmetry element that we're going to be covering in this video is an SN rotation, also known as an improper rotation. All this is essentially is just a rotation followed by a reflection, leaving the molecule apparently unchanged in space. So a good example of a molecule that expresses this be methane, although I'm not going to be showing you guys this in this video. I'm using a household object that I chose, which is a dumbbell. And if we disregard the 15s on the side of this, we could see that this expresses S6. So I could rotate this by 60 degrees and then reflect it, and it appears unchanged in space. It's also significant to note that something that shows S2 is also the same as an inversion center. The final symmetry element that we're going to be covering today is an inversion center, also known as a center of inversion point. This is where you have a molecule that every atom could be pushed through the center and out an equal distance, and it appears unchanged in space. Note that this is the exact same as a S2 rotation, where it's a C2 rotation plus a reflection. So, a real-world example of this using a molecule would be hexafluoroantiamate, but we're not going to be using that today since we're using a household object. The object that I chose to represent this best is a yo-yo. As you can see, if we use this little center axis as our inversion center, each point could be pushed through the other side and it'll appear unchanged. And I could prove this by showing you guys an S2 rotation. So if you see I rotate this 180 degrees and then give it a reflection, it appears unchanged in space. This is very significant to understand.
In conclusion, we have shown here exactly how you can use household items to represent the 5 different symmetry elements and the operations that follow with each symmetry element. Using the fire extinguisher for identity, leaving it in the original position, the n-fold proper axis rotation using the toilet paper roll, the mirror plane using the calculator case, the inversion center with the yo-yo, and finally the n-fold improper axis with the dumbbell. Thank you.